Okay, the next thing we're going to be going into is understand how sound is synthesized electronically. Synthesis is perhaps one of the most important parts of this course in my mind because you understand then how sound is originating from an electronic device. Synthesis goes all the way back to the early part of the 20th century. There was a gentleman named Thaddeus Cahill developed something called a telharmonium, which in 1906 I think was perhaps the first attempt of having an electronic device that you would add up the sounds together and to try to synthesize something larger. So let's understand what we're doing when we're trying to synthesize sound. If we go back and take a look again at our overtone series, which we talked about before, remember the overtone series is a series of vibrations that happen off a fundamental. When we make a pitch and we hear that pitch, we're hearing the fundamental, which is the first. Let's say I have a low fundamental here. That might be the low C on a cello string. When you hear that low C cello string, you're hearing that pitch in your brain, but you're actually hearing all these other partials that are resonating, plus many other partials which aren't part of the overtone series. But if we look at the ones that are being generated from that pitch, that's what gives us the sense of timbre, remember. So if we want to reverse this process, how would we try to synthesize the sound of that cello? What we would have to do, one approach would be what is called additive synthesis, where we would take each of these vibrations in the overtone series, and we would measure what the cello sound is. So we might find something where the second overtone may have that amount of amplitude. The third, which is the G, might have a little bit less. The fourth partial might be a little more. So what you end up with, as you go up the overtone series, you start to see varying amplitudes of each of the partials, and usually they get softer as you go up. Some of them may not be present, some of them might be. And of course, what makes all of that happen is the material of the wood itself of the cello. So if you change the material, then you change which overtones are there and the amplitude or the loudness of them. So if we were to measure and analyze our cello sound, for example, we would find a particular spectrum of various kind of frequencies and overtones and their amplitudes. So then if we reverse that process, we could take each of them individually. They're what are called sine waves. A sine wave is a waveform which contains no overtone or partials in it. So each of these would be a sine wave. If we tried to do additive synthesis, we would need multiple sine wave oscillators, something to generate sine waves, assign them to those frequencies, and then assign them to the particular amplitude. And over time, if we had enough of them, it would start to sound like a cello. So additive synthesis is the idea of breaking down the sound, analyzing it, and then trying to recreate it using individual sine waves to mask or to model the particular relationship of that particular spectrum. So if we had enough sine waves, we could make an interesting sound that would sound very close to a cello. Obviously, the number of overtones on a cello playing a low C that we're listening to is a large number because, remember, the overtones go all the way up to our hearing range, which is up to 20,000 vibrations per second, 20,000 hertz. So we would need a kind of a large number of sine waves in order to approximate that original sound. So when composers and engineers in the early part of the 20th century first started exploring how can we actually synthesize sound, they didn't have access to that number of sine wave oscillators, obviously. So we end up developing other kinds of procedures for synthesis. So what we'll talk about in this section of synthesis is all the different ways that you can use synthesis. There's additive synthesis, subtractive synthesis, which is where you take complex waveforms which have a lot of spectral content in them, and you start to filter some of that out, and that way you get other variances through subtractive synthesis. But we'll also be able to make up sound through what's called frequency modulation or amplitude modulation. We can develop other kinds of sonic possibilities. And then later we'll get into granular synthesis, wavetable synthesis, and then what's called physical modeling, where we take a physical sound of acoustic sound and then try to recreate the parameters of that physical aspect. So there are many different approaches to synthesis, but what I want to do in this section is give you the fundamental basis for how analog synthesis originated, because then the parameters of that synthesis will apply toward any kind of software program that we'll be learning through the rest of the course. There are programs that I want to introduce you to later in the course, which are programs where you can build up from scratch any kind of parameter of sound design. And those are not ones we're going to be covering in this class, but that's ones I want to introduce you to that maybe you can later on learn on your own, because that's where you really get power to develop anything you want in synthesis. And that's what a lot of the people in the field who are the professional sound designers and composers utilize these particular software systems. And that's, for example, Max MSP is a commercial one. There's a free one which I'll introduce you to in the last part of this class, which is called Pure Data, or PD, which is based on some of the design principles of Max MSP. And that's the one that I would suggest that you take a look at, because you can do a lot of your own synthesis systems in that software. But today, let's talk about what are the fundamentals of synthesis. If we take a look at a website that you can download, wikibooks.org is a site which has some open access information. This is sound synthesis theory. And it'll take you through some of the basic aspects of what we're trying to cover today in synthesis. So in synthesis, we will be having oscillators, which will create the vibration source. Those oscillators can be different kinds of spectral content in them. And we will talk about the 4 primary oscillators that you will find on most analog synthesizers. And then from there, we will move into processing that waveform. And usually that's called a signal modifier of some type. So signal modifiers can be filters where we extract or attenuate some of the content, or we can have envelope generators which give us a time variant or time domain change of some of the parameters, and then we'll have amplifiers and other kind of signal modifiers. So if we take a look at oscillators, that's the sort of beginning part of synthesis. Originally, the analog synthesizers came in 4 different varieties. So if we talk about the first one, was called a sine wave oscillator. A sine wave, and the symbol for that, it sort of looks like that when you see it on an oscilloscope. And the sine wave, the definition of a sine wave oscillator, it's just a fundamental frequency, and I'll abbreviate here, a fundamental frequency with no partials. So this would only be the number 1 of our cello. If we were to take out everything else and have just the fundamental frequency that we're listening to, that would be a sine wave. There are actually no sine waves that occur in nature because by default, anything that's vibrating in nature has a material behind it that makes the vibration. And that material is going to give you qualities of overtones in it. So the sine wave is something we can produce electronically, but we won't be discovering sine waves in nature. Perhaps if you hear a Western orchestra, the instrument that might be closest to a sine wave, but not really because they're more materials, would be a flute. Even a recorder, a Renaissance recorder, would be closer to a sine wave because you have less partials in there. But that's as close as we can get to a natural instrument to a sine wave. So the sine wave is an important waveform that we'll be using in our oscillations. So that would be the first one. The second one is a triangle waveform. The triangle waveform usually is abbreviated with just a triangle. The definition of a triangle is we have the fundamental frequency, again, I'll abbreviate, fundamental frequency, but we also have the odd numbered partials so in this case, we would have 1, 3, 5, 7, 9. So if we look at 1, and then 3, 5, 7, 9, all the way up. So you take just the odd number partials, but they have an amplitude relationship of 1 over n squared. N is the partial number. And I'll abbreviate here, sorry. So if we think about what are the, let me go back and maybe get rid of this. 1 over n squared means that each partial that's present in our sound will be divided by the partial number squared. So let's say, for example, we have a frequency, and I'm just going to say my fundamental is 20 hertz, and it's, say, at 100 decibels, just to make this simple. So to calculate a triangle waveform, we have the odd number partials. So the next partial is going to be the third partial, which would be 3 times the fundamental frequency, which would be 60 hertz. And its amplitude relationship is going to be 1 over n squared. So it'll be 1 over 3 squared. So it's going to be 1/9 of the amplitude of the fundamental. So the amplitude of our fundamental was 100 dB in this case. So we would take 1/9 of that, which puts us about the 11 dB. So then the fifth is going to be 1 over 5 squared, which puts us about 4 dB on the fifth one. So you can see in the triangle waveform, if we were to connect the dots on this, there is very little amplitude on the partials. It's just the odd number partials, and their amplitude is very low. So when you hear a sine wave and a triangle waveform, there's very little difference in the sound. So let's listen to the difference of those sound waves quickly. I'm using a commercial software program for today just to demonstrate this. But if I listen to a sine wave, that's the sound of a sine wave. So if I pull up then a triangle waveform, you can hear just a little bit difference in the sound. That brighter sound means that we're hearing those odd number partials along with that. Once again, the sine wave and the triangle. So very similar kinds of qualities of sound, not a big difference there. The overtones that are present in this are in an amplitude relationship of 1 over n squared, and that's the sort of important part of that. Okay, next, and we will find the triangle and sine wave used for different purposes in our synthesis patches. So let's try for the next one. The third kind of waveform that you would find on synthesizers is, and I'll give this a category first of all. This category is called pulse waves. A pulse wave, usually the symbol for that is something that looks like this. A pulse wave is a category of waveforms. The most common one is called a square wave. And a lot of times people just refer to it as a square wave. But a square wave is one type of pulse wave. The definition of a pulse wave or square wave is a fundamental frequency with odd numbered partials in an amplitude relationship of 1 over n, n being the partial number. So it's the same number of overtones, but this time the third, fifth, seventh, ninth partials. If we take 1 over n, 1/3, so the amplitude of the third partial is going to be 60 hertz, but a third amplitude of 100 would be 33. So we get a much louder quality of overtone there, and the fifth. So when you add these up, there is much more amplitude in the waveform, so that there's a significant difference in the sound. So if we listen now to the sound of, go back to the sine wave again. Here's the triangle. Now if I listen to the square wave or the pulse wave, so now you hear much brighter sound because the odd number partials are much louder than they were in the triangle waveform. So the square wave is a very interesting waveform because there's a richer quality of sound that we can then later, if we want to take these complex waveforms, which have quite a bit of spectrum in them, we can filter some of the sound out, and that's what gets us into what's called subtractive synthesis. So you create these very complex waveforms which have a lot of spectral content in them, and then as we take out certain of the overtones or reduce their qualities, we can then make other sounds, and that's where that's called subtractive synthesis, is when you reduce the content of complex waveforms. Now I did mention that the square wave was one type of pulse wave. The reason that we have this category is that this particular waveform has one other variable that we can change in it, and this will be important later on. And this variable is what's called the duty cycle. The duty cycle is the relationship, the ratio of the compression to the rarefaction. Remember, we talked about a waveform as having this sort of energy of a compression, and then there's also going to be a rarefaction. It's a combination of those two that give us the vibration source that we can hear, the energy that is pushing and releasing. Well, most waveforms, you have a ratio of the length of the cycle to the compression is usually a 2-to-1 ratio. That's the standard duty cycle of most waveforms without any variance. The compression is exactly 1/2 the length of the cycle. Well, the pulse wave, you actually can vary that. So if you have a square wave is a case where the ratio is a 2-to-1. So a square wave, you get exactly the same distance between the compression to the rarefaction. So the ratio of the whole cycle to the compression is 2-to-1. But in a pulse wave, we can vary that, and that's called the pulse width. So in pulse width, we can change the ratio, say, to 4-to-1 or 8-to-1. So when you do that, you will be taking out some of the overtones. So as I cross, let's say if I can explain this, normally you have, when a vibration crosses there, that's a 2-to-1 difference in the ratio. If I were to have something where I crossed 3 divisions, you have 2 nodes here. And if I move my duty cycle to where the ratio is 2 or a third of the whole length, when you move your duty cycle to that point, you cancel out whatever overtones are at that point. So in this case, this would be my 3rd overtone. I would cancel out that particular overtone, so which changes the timbre. Anytime that you vary the spectrum, you're going to be changing the timbre. So in this case, the duty cycle change that we have in the pulse wave, as we move that, we hear slight timbre change because we're going to be canceling out some of the overtones as we hit those particular ratios. If this is too confusing, don't worry about it. We'll explain this a little bit more later. But the concept here is that what we're trying to do with these waveforms is to give us some variance of timbres. And the square wave is a fixed duty cycle of 2-to-1, but the pulse wave, we can move that in, and it's no longer a square wave, but it's the same content of odd partials and a 1/n relationship. But we can now cancel out some of those partials by moving the pulse width. So now let me move on to the final one, and I'll erase some of this here. The final one is going to be a sawtooth waveform that we will find in all analog synthesizers. And the sawtooth is, here again, one of the more complex ones that'll give us a lot more spectral content. So if we look at the 4th one is called a sawtooth, and the symbol for that, and they can be drawn 2 different ways. You can have it ascending, or sometimes it's descending. You can have a descending sawtooth, either way. So the definition of a sawtooth waveform will be a fundamental frequency plus all partials in an amplitude relationship of 1/n. N is the partial number. So in that case, remember the square wave, we had the odd numbered partials in an amplitude relationship of 1/n. The difference between the square and the sawtooth is we have all the odd, plus we have the even numbered partials in the same relationship. So in that case, we would go back and add number 2, and the amplitude of this would be 1/2 times the amplitude of the fundamental, which would give us 50 dB, so forth. So you get the combination of the square wave, plus we add the even number partials in that. So if I go back to my example here, let's listen to these again. So here's the sine wave. The sine wave, remember, is fundamental frequency with no partials. And then we hear the triangle, which is a fundamental frequency with odd numbered partials in an amplitude relationship of 1/n squared. So we get a little bit of timbral change. Then we move to the square wave or the pulse wave, which is odd partials plus 1/n, so a louder amplitude. And then we get the sawtooth, which is all partials in an amplitude relationship of 1/n. So you can hear the timbre as it gets richer. It sounds perceptually maybe brighter. Some people say those are brighter sounds than the sine wave. It perceptually gets louder also, because we're not hearing actually a change of volume of the fundamental. The fundamental is staying exactly the same volume. But it's the perception that all these other vibrations, their volume is making it sound louder to us. But we're not actually changing the volume, we're just changing the spectral content of that. So those are the primary waveforms that we'll be working with. Once again, sine wave, triangle, square, or a type of pulse wave, and the sawtooth waveform.
The preceding program is copyrighted by Emory University.